Okay, today's video is about the rectifier. All these components in front of us are rectifiers. You will recognize this component here as a diode, and a single diode. It can also be called a rectifier because its function as a semiconductor is to allow current to flow in one direction but not the other direction. The side with the line on there is our cathode, or kind of view of it as our negative side, like the wall. Current is going to flow one way, but it will not flow the other way through our diode. These other components basically have diodes built into them, essentially 4 diodes. Each of those rectifiers are known as full wave bridge rectifiers. Each of them function exactly the same. They have different power, voltage, current relationships, and can handle different amounts of energy. For our lab, we will be using the diode. We're actually just going to be using 2 diodes to create a full rectifier, but you could also use 4 diodes to create a bridge rectifier. We're going to be referencing the textbook page 388. Goes over, this is chapter 11 in our Cook textbook. Goes over the power supply and specifically the aspect of rectification of the waveform. So here you see our transformer. When we have one diode oriented in the transformer, we only see the positive alteration of the AC wave through that diode. And so we're going to look at that on the oscilloscope, where we have both the positive and negative alterations of our sine wave. Okay, and when run through the rectifier, we end up with a pulsating DC waveform where only the positive alteration is seen, and then we have the flat. So what might that look like on our circuit board? Over here, it appears I have 2 in there. I'm actually only running the 1 right now. This diode has been disconnected, but what I have is a center tap transformer. This is a split center tap transformer where our red wires are an 8-volt AC output, and I just simply have it powering the lamp there. We're going to be focusing on the yellow wires and the blue wires. So the yellow wires and blue wire are a center tap section of this secondary coil here. We are splitting the voltage relative to the blue as our ground or common here, and so taking that secondary voltage, splitting it in half, half of it on one yellow-blue combo, the other half on the other yellow-blue combo. Those yellow lines have been tied into this bus line, and so we see one diode coming off of one of those bus lines, the other diode coming off the other bus line, to give us what eventually will be a full wave rectification signal. And here we have just simply a load. This is a 10K resistor, just representing a load on our power supply. We have our diode, we have a load. That diode is tied to the positive bus line over here, and the load is across here. This is the negative side of that into our ground. And so our oscilloscope probe is hooked into what essentially represents the output of our power supply or rectified waveform. So when looking at this whole circuit on the oscilloscope, currently we see half wave rectification. And so we're looking here at our settings. Our channel 1 setting there is set at 5 volts peak to peak. So when you look with a DC sense here from our flat baseline of 0, or 5 squares, 1, 2, 3, 4, we're approximately 24 volts from a 0 to peak in this half wave rectification. So what we see is the positive side of the alteration. The diode is cutting out the negative side of the alteration, and then it begins its positive cycle again. Our time per division, we're looking at this waveform up here, looking at the time settings. We're currently on 2 milliseconds per division. So there would be 20 milliseconds represented across this entire graph here. And if you remember back, the frequency of our AC wall source value is